Okay, so here we're going to look at the events of the action potential in the neuron. What we have just seen is that in the dendrites and in the soma, we have a short distance electrical signal that's created when the neuron is stimulated, and we call that short distance electrical signal a graded potential. Right? And that only occurs in the dendrites and in the cell body, or what we call the soma of our neuron. Okay? But recall that I also said that neurons have very long axons, and these axons can sometimes be as long as 3 feet. So we need a good long-distance electrical signal that's going to carry our message from this neuron to another cell. Right, so what happens is that our graded potential, our short-distance electrical signal in our dendrites and in our cell body, creates a long-distance electrical signal called an action potential in our axon. Right, so we're going to take a look at how that works and what the events of the action potential are. Okay. So our action potential is only created or formed in one specific region of our axon, and that's the region called the axon hillock. Remember, that's this cone-shaped region that connects our axon to our neuron cell body, or our neuron soma there. All right. So the action potential strength, or the electrical signal of the action potential, does not decay with distance. So it's a really good long-distance electrical signal. And what I mean by doesn't decay with distance in that the electrical signal of the action potential regenerates itself as it moves down the membrane. Right. So what it does is an action potential in one small part of the membrane will generate a new action potential in an adjacent region of the membrane. So the signal stays strong no matter how far that signal has to travel or to go. In order to create an action potential, though, the voltage at the axon hillock must reach a very specific value. That is, the membrane voltage must reach some very specific level before an action potential will be created and move down the axon. And we call that very specific voltage, we call that threshold voltage, or simply, if you just want to refer to it as threshold, that's fine. Right? This threshold voltage, if we were to actually put, here we've got a little voltmeter here with our readout. Recall that resting membrane potential in a neuron is somewhere around minus 70 millivolts. So, and threshold voltage is about minus 55 millivolts, which means that our membrane voltage needs to rise. It needs to become more positive by about plus 15 millivolts. So it needs to go up a little bit in order to create or in order to reach threshold and create this action potential. Okay. So in that case, because the membrane voltage needs to become a little bit more positive, our membrane voltage needs to depolarize a little bit from resting membrane voltage. Okay. If our graded potential in our in our soma or in our dendrites depolarizes the axon hillock and it reaches threshold, then the axon hillock will create an action potential. And this action potential will spread the entire length down our axon. Okay. All right. So a graded potential that depolarizes our membrane towards threshold, or brings our membrane voltage closer to threshold, is called an excitatory postsynaptic potential. So this is a very specific term for a graded potential. Okay. So a graded potential that depolarizes our membrane closer to threshold is going to be called an excitatory postsynaptic potential, or EPSP. And so we can see that on the graph here. We can see that in our graph here. Our membrane potential is on our vertical axis here, and our time in milliseconds. We were measuring the voltage over time, or the voltage change over time in our neuron in milliseconds, so 10 thousandths of a second. So this is 10 thousandths of a second, 20 thousandths of a second. And we have some stimulus here. We have some graded potential, and that graded potential brings the membrane voltage closer to this dashed line here, which is going to be our threshold voltage. So EPSPs, or excitatory graded potentials, always bring the neuron closer to threshold for creating an action potential. And the reason for this is that the neurotransmitter that creates a graded potential is opening sodium channels and letting sodium come into our cell here. Okay. In sort of contrast to that, we also have graded potentials that bring our membrane further from the threshold for creating an action potential, and that's called an inhibitory postsynaptic potential, or IPSP. Basically, this is a graded potential that hyperpolarizes or makes our membrane voltage more negative, bringing that membrane voltage further from threshold. Essentially, what this means is an IPSP event will make it more difficult for an action potential to be generated. Right. So we have our membrane voltage or our membrane potential on our vertical axis here, time on a horizontal axis in milliseconds, and we'll initiate an IPSP, or an inhibitory graded potential here. And we see that our membrane voltage dips well below 70 millivolts further away from our threshold voltage here. Okay, so in this case, it's going to be more difficult for this neuron during this brief little time to create an action potential, right? And the reason for this is that the neurotransmitter that creates an IPSP is going to open potassium channels, letting potassium leave the cell. Okay, so our potassium being a positive charge, it leaves the cell. It's going to mean that our membrane voltage is going to become slightly more negative for a brief time. Okay, so IPSPs kind of sum that up. IPSPs always bring the neuron further away from threshold, so an action potential is going to be much less likely to occur there. Okay, so we've looked at the stimuli that create action potentials. We'll now actually kind of turn our focus for a second to the action potential itself. And one of the things that's really interesting about the action potential is that as long as a stimulus reaches threshold, an action potential, if we measure the change in membrane voltage, it'll always be exactly the same no matter how strong that stimulus is. All right. So in that stimulus intensity, that is, if we have a really strong stimulus, it's not going to affect the intensity or the strength of our action potential. So what we're seeing here is that on this particular, and this is sort of a two-part graph here, we're measuring membrane voltage or membrane potential in a small part of the membrane, right? And we're gonna artificially create a stimulus that doesn't quite reach our threshold voltage here in our neuron. And so what we see there is that if a stimulus doesn't reach threshold at all, there is no action potential, so there's no change in our membrane voltage from rest here. Okay, so no stimulus. If stimulus doesn't reach threshold, no action potential. Right, so keep that in mind for the next slide here. So what we'll take a look at next is we'll take a look at what happens when the stimulus does reach threshold. Right, so we've got two stimuli here a little bit later on. One just slightly goes above threshold, and one goes way above threshold here. So we've got two stimuli that exceed threshold in different ways. Right. Action potentials will always occur. That is, the membrane voltage in an action potential will always go from minus 70 millivolts to about plus 30 millivolts at its peak and back down to minus 70 millivolts if a stimulus reaches threshold. And it doesn't matter that this stimulus here was stronger than this one. Both of these groups or series of action potentials here, so each of these vertical lines here represents one action potential. We see that these action potentials reach the exact same height in our graph. That is, they reach the exact same voltage as the action potentials that occurred during a really strong stimulus. So action potentials will always occur if a stimulus reaches or exceeds threshold. Really, the main difference that we see between these two is our really strong stimulus on the far right here simply created more action potentials per unit time. A weaker stimulus that still reaches threshold still created action potentials, but it didn't create as many in the same amount of time. All right, this phenomenon, or this phenomenon where an action potential will either occur if a stimulus reaches threshold or will not occur if a stimulus doesn't reach threshold, is called the all or none phenomenon, right? So, and it states really that action potentials will always occur when a stimulus reaches threshold, and an action potential will never occur if a stimulus doesn't reach threshold, right? Pretty straightforward, I hope there. Okay, so we have the all or none phenomenon. Okay, so now let's look at what are the events of the action potential? What's actually happening during the action potential? How does the membrane voltage change? What what structures are involved in creating action potentials, right? Action potentials are really created by two ion channels in the plasma membrane of our neuron, right? And these ion channels are sodium and potassium channels. And these are called voltage-gated channels because they only open in response to a change in the membrane voltage, right? They are highly abundant on the axon, right, where our action potential is occurring, the axon hillock, which creates our action potential, right at the interface between the soma of our neuron and the axon terminal, that is the very end of our axon. Okay, so they're very, very abundant there. They're not found, however, on the dendrites or the soma. That's where those chemically gated channels are found that respond to neurotransmitters are. So there's still an electrical signal being created by the dendrites and the soma. It's just created by a different stimulus, right, by the neurotransmitter or another stimulus, right? And like I said, these open in response to changes in membrane voltage. And so we have two kinds. I mentioned that they were sodium and potassium channels. We have what's called a voltage-gated sodium channel. When these open, sodium is allowed to diffuse into the cell, so it brings positive charge in, making the membrane voltage rise quickly to a more positive value at the beginning of an action potential. And we have voltage-gated potassium channels, which open up at the very end of an action potential, and when they do open up, they allow potassium to diffuse out of our cell and restore the negative resting membrane voltage. Right. So let's look really quickly at, or really briefly at, voltage-gated sodium channels. As I mentioned before, when these guys open, they're going to let sodium diffuse into our cell. So remember that sodium is in high concentrations on the outside of our cell at rest. So when these channels open, sodium is going to diffuse into our neuron and bring positive charge with it. Okay. These open first at the start of our action potential. So what happens at the beginning of our action potential is we'll see the voltage rise very quickly from a minus 70 up to about plus 30 millivolts very, very rapidly. Voltage-gated sodium channels are actually really, really complicated in how they work, in that they have three configurations that they can adopt during the action potential. They have what's called the closed configuration. They have an open configuration, which just lets sodium in. And then they have this other configuration. It's called inactivated. And we'll look at these three configurations right now. All right, so we'll start with the closed configuration. So let's look at our very beautiful voltage-gated sodium channel that I've illustrated here in PowerPoint. We have our plasma membrane here, so it's embedded within our plasma membrane, and it has a channel through it, through which sodium, when this channel is opened, sodium can diffuse from the outside of our cell, which is the top part of our plasma membrane here, into our neuron here, at the bottom part of our diagram here. And these essentially have two pieces. These vertical blue bars here are what are called the channel, so it provides a passageway through the plasma membrane. And then it has these two horizontal structures in red here called the voltage gate. This is the structure that opens and responds to changes in membrane voltage and opens, permitting sodium to diffuse into our cell. And then they have this sort of piece, it's a protein piece that's kind of chained to one of the voltage gates. It's called the inactivation gate. Right, so we've got kind of the pieces. We'll see how the pieces work together. All right, so in the closed configuration, right, we've got sodium in high concentration on the outside of our cell. Sodium is not going to be permitted to enter our cell, so it's really, I think, really kind of straightforward there in that it's going to prevent sodium from diffusing into our cell through this channel, right? This voltage gate, though, will open if a stimulus, that is, if an excitatory postsynaptic potential, an excitatory graded potential, creates a stimulus that reaches threshold. That is, if our membrane voltage is brought to threshold, this voltage gate will open and let sodium diffuse into our cell. Right? So that's what the open configuration is. So in this configuration, our voltage gates have moved. Our sodium is now permitted to diffuse into our cell. All right, so that's going to bring positive charge with it, and so what we'll see is our membrane voltage rise very quickly to about plus 30 millivolts here. So the membrane in this small part, or the voltage in this small part of the membrane, will become positively charged. Here, very briefly. And then we have, right after it opens, we have the voltage-gated sodium channel very quickly adopts this inactive configuration, where our voltage gate is still open, right? So our voltage gate has not sort of closed yet, but what happens is that this inactivation gate swings into the opening of the channel and blocks it. Okay, basically what this configuration does is it's functionally the same as a closed channel. It's not going to let sodium diffuse into the cell. But one really kind of special thing that it does do is that if there is another stimulus that occurs while the voltage-gated sodium channel is in its inactive configuration, is that this channel will not open again. So it doesn't matter if that stimulus reaches threshold, it doesn't matter if that stimulus exceeds threshold, it doesn't matter how strong that stimulus is. This channel is not going to open again until it can reset back to its closed configuration. So basically inactivated, it's just not going to respond to any stimulus while it's in the inactive configuration. So it's effectively, in the inactive configuration, it's effectively preventing sodium from getting into our cell there, right? So the channel, like I said, must reset to a closed configuration before it will open again, before a stimulus will cause it to open again, right? Okay, so that does it for voltage-gated sodium channels. Let's take a look just briefly at voltage-gated potassium channels before we actually talk about the events of the action potential. Voltage-gated potassium channels a little bit more straightforward in terms of their configurations. They really have two major configurations, the open and the closed configuration. So we've got our plasma membrane here again, and we've got our voltage-gated potassium channel. Okay, and so we have the channel itself, and it also has a voltage gate, but notice it has no inactivation gate over here, right? So when these guys open, or when these particular channels open, they're going to allow potassium to diffuse out of our cell. So recall that potassium is at high concentrations on the inside of our cell, and if these channels open, it will diffuse out very rapidly, taking that positive charge with it and making our membrane voltage more negative. Okay, these also open last during an action potential, so they're kind of slow to open, and they always open last during our action potential, right? And as I mentioned, there are two configurations, open and closed. We just saw the closed configuration here, which I pointed out the channel here, and also the voltage gate, which we saw. The second configuration that we'll take a look at is the open configuration, right? In which our voltage gates here will open up and allow potassium to diffuse out of our cell, taking positive charge with it. Okay, so voltage gate is open, potassium leaves our cell. Alrighty, so we've looked at the major players involved in the action potential, so let's look at the events of the action potential itself, right? So what we're going to do, just like with everything, we'll put a small voltage meter in a small section of our axon plasma membrane here, and we'll simply measure the change in voltage during an action potential as the action potential occurs in that little part of the membrane, right? And we'll see essentially four major events. The cell will go from rest, the voltage will climb very rapidly, the voltage will then decline very rapidly, and then the voltage will start to even out back towards resting membrane potential. So we'll look at all four of these events in sequence right now. Okay, so we have our cell that's at resting membrane potential, so our voltmeter is not registering a response yet to a stimulus. So in our upper left-hand corner here, we've got our graph of membrane voltage during action potential. So we've got on the vertical axis here, we've got our membrane voltage. On our horizontal axis here, we have time and this is in milliseconds, which is thousandths of a second. So this is 1/1000th of a second, 2/1000ths of a second. And you can see that this event happens in about 3 or 4 milliseconds, so 3 or 4 thousandths of a second. So this happens very, very quickly. This is a very quick, very brief change in cell membrane voltage. All right, so we're looking at the resting membrane potential. Our cell is currently at rest, which means our cell has not been stimulated yet, which also means that our voltage-gated channels, that is our voltage-gated sodium channel here on the left, and our voltage-gated potassium channel here on the right, is closed. So they're both in the closed configuration, but they will open if a stimulus reaches threshold. Okay. The only thing that's active at this point in time are the leak channels that permit sodium and potassium to diffuse across our cell, and the sodium-potassium pump, which maintains the resting membrane potential. Those are the only two channels that are actually seeing substances move across them at this point in time. I will point out too that these channels never really stop working before or during an action potential. So these channels are always seeing sodium and potassium moving through them. All right, so now we'll take a look at what happens when the cell is stimulated, right? So a cell is going to receive a stimulus that depolarizes it. So that is, our stimulus is going to be an excitatory graded potential or another action potential further up the plasma membrane, right? So our membrane voltage after the stimulus is going to start to rise toward threshold, and then after threshold it'll create an action potential, right? So we have our stimulus. At this point, the stimulus means that sodium is going to enter the cell, and it's going to move into close proximity to our voltage-gated sodium channel here. So sodium comes into the cell. It's going to diffuse away from where it entered and towards our voltage-gated sodium channel here. So you're probably asking yourself, where did this sodium come from? Right. It could have occurred during the first part of an action potential a little bit further up the membrane, so a voltage-gated sodium channel could have opened further up the membrane that we didn't see, or an excitatory graded potential, an EPSP, being created in the soma or the dendrites. Okay, so we've got our stimulus. So now we'll say that stimulus reaches threshold, and now we're going to take a look at the first event of the action potential here. Okay. So the first event of the action potential is that our membrane voltage has reached threshold. So that means that our membrane voltage is sufficient to cause the opening of voltage-gated sodium channels, and our voltage will rise very quickly during the first part of the action potential. And this first part of the action potential is called the depolarization phase, or it's represented by the uphill part of our graph here. So recall that depolarization is when membrane voltage moves towards zero or becomes less negative. Right? During the depolarization phase is when voltage-gated sodium channels are opening and letting sodium come into our cell here. So we're seeing a rise in membrane voltage because our voltage-gated sodium channels are letting sodium come into our cell. So sodium is going to enter the cell. The membrane voltage is going to rise rapidly and become positive. One thing to note here is that when the membrane voltage rises and reaches about 0 millivolts, the voltage-gated sodium channels start to become inactivated. Okay. While they're inactivating, so they don't inactivate immediately and snap closed. This little inactivation gate will swing and plug up the channel here. They don't do that immediately. It takes a little bit of time for them after 0 millivolts to begin becoming fully inactivated. So while that's happening, a little bit of sodium continues to enter the cell, and our voltage will eventually peak at about plus 30 millivolts here. All right, so we've seen the beginning of the action potential. We'll now look at the end of our action potential, which is called the repolarization phase. It's represented by the downhill part of our graph here. There's a couple of different things happening during repolarization with both channels, with both voltage-gated sodium and voltage-gated potassium channels. First of all, voltage-gated potassium channels are going to open. So they're going to the incoming positive charge that was that came in to our cell, that sodium came into our cell, bringing positive charge with it, was the stimulus that opened our voltage-gated potassium channel here. Okay, so our voltage-gated potassium channel opens. Potassium is going to leave the cell, and potassium being a positive charge means that potassium leaving the cell is going to rapidly drop our membrane voltage back down towards resting membrane voltage. Right? So our membrane voltage is returning to rest as potassium leaves the cell. Okay. One thing that I wanted to mention here too was that the voltage-gated sodium channels are now inactivated, so sodium can no longer diffuse into the cell through this channel. Last but not least, our final phase of the action potential is this little dip and return to resting membrane voltage at the very end of an action potential called hyperpolarization. And this is kind of an interesting phase in that it really results from the fact that at this point, when our voltage-gated potassium channels begin, or when our membrane voltage reaches resting membrane voltage again. That is when our membrane voltage falls back down to minus 70 millivolts. Our voltage-gated potassium channels are going to begin closing. They don't close immediately. It takes them a little bit of time to close. And while they're closing, after membrane voltage reaches minus 70, a little bit of potassium continues to kind of diffuse in the cell as the channels are closing. So our membrane voltage actually overshoots resting membrane voltage by a few volts. So this voltage can be as low as maybe about minus 80 millivolts. So our resting membrane voltage is overshot a little bit with hyperpolarization here. Also during this phase as well is when our voltage-gated sodium channels reset back to their closed configuration from the inactive configuration.